anything affecting that membrane thickness, what we're going to find, oxygen is usually lower than carbon dioxide in the lungs. And if we have something affect that membrane thickness, we've now affected the pressure of my oxygen, and I'm going to have some trouble moving that gas. Think, for example, people who might get pneumonia, all right? And one thing that happens is a thickening of these respiratory membranes, because it's the mucousy type of stuff, okay? And people who have pneumonia, how do they normally feel?
Cold. Like there's a weight on their chest?
Okay, like there's a weight on their chest, that they can't get enough of the oxygen in, and that sort of thing. And the problem is there has been an effect to their membrane, and they're not getting because that red blood cell, at the point where that red blood cell is coming through that capillary, remember, it's all squished, okay, moving through, all right? And if it takes even longer for the oxygen to diffuse across that membrane, okay, there's going to be even less getting picked up. So it's going to feel like they're not getting enough, if that makes sense, okay? The membrane area, one of the diseases that we've talked about that destroys the area of this membrane because of what it does. It, makes that alveolus one great big huge grape rather than a bunch of small ones. The emphysema, and then lung cancer. Lung cancer will once again affect this movement and this flow of the air because parts of the lung are dying. We have what's termed ventilation perfusion coupling. If you couple something, I think about my plumbing, and I have to go buy a coupling to put the two pipes together, okay? So if I couple something, I'm putting it together. So basically, this is the physiological response to matching airflow and blood flow. If we have areas of the lung that are damaged, they can actually shunt the blood to other areas of the lung to be ventilated, and this happens. It happens, for example, if someone's got pneumonia, okay? Because we've got the smooth muscle, all right? Basically, to match airflow and blood flow, it'll take it to another area of the lung to be ventilated. Now, this can begin to take place quite a bit in areas where diseases might be showing up. One of the reasons that I mentioned emphysema is progressive, because when it's first starting, okay, you begin to, you're not noticing it as much. Blood's getting shunted to other areas of the lung. We're getting the ventilation, and we're still breathing, okay? But like I said, there's no cure. So for emphysema, the disease can only progress, all right? And it's going to progress to the point where you're not going to have a match between airflow and the blood supply.
So is that like, if there's a tumor on someone's lungs, is the blood shunted away from that?
Yeah, it'll be, now, wait a minute. Because cancer is a cell that is surviving off of blood flow, because it's cells that don't stop, they just continue to move and grow and this sort of thing. If a cancerous cell doesn't get the blood flow that it thinks it should be getting, it'll actually signal and the body will produce more vessels to get there. Yes. So with lung cancer, it could still be blood flow, but the blood flow is not going to the lung that's getting ventilated. It's going to the cells that are now cancerous. Yeah, cancer cells do this constant division. They never stop, okay? And one of the things they do, they actually, they promote more vascular creation so that they can get more and more blood flow. It's really cool. Not cool, but you know what I mean. Yeah. So the alveolar gas exchange, we're dependent on those pressures. We are dependent on the structure. We're dependent on how easily a gas dissolves in a fluid. So if we begin to look at the oxygen and the carbon dioxide, we know that oxygen, that it binds to hemoglobin. And in the red blood cell, do you happen to remember the structure of the hemoglobin? It's a quaternary structure, so meaning you've got the 4 chains together. In the middle of each of those chains, we have what? The heme group, okay? We've got the iron. Oxygen attaches. So this tells me that for every hemoglobin that's in that red blood cell, it can carry up to 4 oxygens. If it is carrying all 4 oxygens, we would say that it is 100% saturated. When the hemoglobin is attached to a molecule of oxygen, we say that it is oxyhemoglobin because it has oxygen. These numbers right here. Ever seen or heard maybe that 100% saturation anywhere?
Red blood cells, when they test you, like,
They put the little thing on your finger?
yeah.
The O2, the what thing?
O2 stat.
The O2 stat thing. Okay? Some people have to walk around with them. I think they make them now where they're like just
To go on your finger.
go on the finger and
Like Band-Aid looking ones.
Yeah.
Strapped to you.
yeah. And then, you know, if you're in the hospital, they clamp the thing on you and everything, you know. And it's reading, it's really cool. I looked up one time, oh man, I can't remember exactly how it's reading the oxygen levels at the tip of your finger. Because that always boggled my mind. Oh man, I looked that up and it's totally gone out of my head now. Anyway, so if one of those hemoglobins is carrying 4 oxygens, we're at 100% saturation. If one hemoglobin is only carrying 3 oxygens, we say it's 75% saturated. 2, 50%, 1, 25%. If we don't have any oxygen bound to a hemoglobin, it's termed deoxyhemoglobin. They got real inventive in lab that day. Okay, so either oxyhemoglobin, deoxyhemoglobin. The relationship between the two of them is going to be termed the oxyhemoglobin dissociation curve.
The relationship between the oxyhemoglobin and the deoxyhemoglobin. Let's turn that.
Great big huge term. Okay? It's letting us know how the hemoglobin loads oxygen. In your textbook, figure 22.3 is an illustration to look at. the oxygen hemoglobin curve. Hold on, did I get the wrong number?
The table 22.3?
Hold on, I think it's the figure 22. Hold on, no, I'm off somewhere. Hold on. Hold on. So that's the spirometry, that's Henry's law. Oh, wow. 2223.
22.23.
So I had a 22.3, I was just missing the 2 in front of it. So 2223 is an illustration of the dissociation curve.
That's what you wrote.
Now, here's what happens, okay, for the gas exchange. As we know, hemoglobin is going to be specialized for the transport of oxygen. Note my terminology there, okay? The red blood cell is specialized for the transport of oxygen. Now CO2 gives us a little bit of a problem, okay? However, that's all right because the body has ways to take care of it. So, when there's low oxygen, all right, and a heme on that hemoglobin, the heme group, binds an oxygen molecule, it makes that heme group change shape, and if it changes shape, it's going to want it to pick up more oxygen.
Causes the heme group to change?
Yes. So, if this is the case, and if I can get an oxygen bound to that heme group, it's going to now affect the other 3 that'll be present, right? That was deoxyed, okay? And now it's making it change its shape, and I'm going to be able to pick up even more oxygen. So deoxy affects oxy. Because if that hemoglobin comes by with no oxygen on it, and the oxygen can bind, it makes the other ones change shape and say, "Ooh, give me another oxygen." So as it continues through the pulmonary circuit, it will continue to pick up some oxygen. So the deoxy affects the oxy. Does that make sense? And then depending upon how long that red blood cell can stay at the capillaries will help determine how many oxygens can be picked up. Can it pick up 1? Can it pick up 2? Can it pick up 3? Can it pick up 4?
When this happens, is this bad?
No.
This happens like all the time?
This happens all the time.
Oh, okay.
Because what's going to be happening is this basic connection between the O2 and the CO2, like I said, under the normal conditions, like the normal healthy male, what's occurring is the ability to match all of the demands of the tissues of the body. The overall goal, match the demand or the pH level of the brain.